work. This is good because it's Reutter that have been going for a while now with Theo Johnson-Frick, and it's sort of a bit of a side result somehow, but I think it's sort of a nice package. That's what it is. And let's just get to the offices. So can actually we talk about TQTs. So pretend we don't know anything about TQTs yet, but there are things we can do with them, right? There's sort of, I guess, the you know, this elaboration. So if I have an arrangement TQT, sort of thing you imagine like that is based on n manifold, so I think that's defined on a dimension space time. One thing I can do is I can sort of look at its boundary conditions or its boundary defects, and also sort of n minus one dimension boundary. And more generally, I can look at interfaces or defects between TFTs. So I can get so another TFT E, another dimension E, and I have n minus one dimensional. That's the things. Or domain wall, or defect, or extended operator, however. And a thing I'm supposed to be able to do with these is to stack them together, so fuse them together. And so there is an assumption. I place on the collection of all TFTs, which is the n-dimensional TQTs. And assemble into an n category. In Tn with objects. One, and which is the vacuum of trivia. So just so that this is sort of unified, a boundary condition that's just that treat my TFT address. And moreover, we have a boundary condition between TFTs. That's just an n-1 dimensional TFT. So moreover, I'm requiring that if I take the endomorphisms of this adequate TQTN at once, getting the adequate TQTN. At this point, I just note I should say, if you have a complete model of TQTs in mind, so implementing those or building such a category can be really complicated and hard, depending on the model. But sort of, I think it's fair to say that it can be expected that it's supposed to be. Okay, and the game plan for this talk is to pin down enough reasonable assumptions on TQTN. And maybe I should say not all TQTN, but it's a bit careful and say on a nice and well-behaved subcategory of. So not claiming this, then that's just like all TQTs, but at least you know, serves an interesting fairly large subset of TQTs of TQTN, which specifies the unique. This is sort of a top-down way to get at these. I'm not sort of by hand constructing such category, I'm just writing down some reasonable things that your category should satisfy to a point where suddenly there's just a unique category which has these properties.
Yeah, here you assume this one is n back. So there's a vector space over a complex number.
I have not yet assumed this. So far, just assume there's an. I mean, this will follow in a second. But yes, one is supposed to be n leg or maybe n super leg or something. But I'm not yet sort of mathematically not much. And this is sort of going to be how I want to set up my talk. Is I will put in mathematical assumptions and theorems and definitions. And sort of in between, I say sort of words what I want to say physically, what I mean physically. So here's the first sort of physics side comment, which I write in orange to clarify a little bit what flavor of TGFTs do I have in mind. This is not going. This is the only assumption I've made so far. This is just to sort of give you an idea of what are the sort of objects you should imagine. What I have in mind is absolute, meaning with trivialized anomaly. Strained, which one means there is no space-time symmetry. Non-unitary, discrete, and very defined and non-manifold. It's defined everywhere. Sometimes this is called compact. Completely, this will sort of turn out to be a synthesis assumption. So let me sort of comment a little bit on this absolute assumption. And absolute, if you then want to talk about TGFT-driven anomalies, people here in the audience are very familiar with that. You do it by sort of looking at negligible on higher dimensional TFT and some relative to it. So that's sort of not that. That's just, I mean, I have to start somewhere, but you can sort of extract anomalous TFTs once you understand these. Frame is easy to lift. There's just a decent problem. Non-unitary, this would be interesting to sort of, I strongly believe there's just a unitary version of this construction, what we haven't done it. And these are sort of more serious assumptions for now, and I'd be very curious to see what sort of happens if you lift.
What is discrete?
So physically means I'm not looking at deformation classes, say, of TGFTs. I'm not looking at sort of what happens if you perturb the TGFT a little bit. I'm really looking at sort of the analog of finite group symmetries. Algebraically. This is all I'm going to do is algebraic. There's no, yeah, exactly.
So the discrete I'm finding is there's a discrete number of object morphism, but there can be infinite number of single objects in morphism. That will allow.
There will be conditions, yes. So this will happen. The way in which those will be infinite is going to be constrained by what comes out of the assumptions. But in principle, yes. So this is something we should put it down.
But the thing that people take some morphism, like instead of infinity, that implies there must be other things that continuous.
Yes, that's right. So I completely agree with this. Is really just pinning down a sub collection of the TGFTs. I mean, I sort of from a mathematical perspective, I just write down axioms and say there's a unique thing later, and then you can sort of think about whether you like the axioms or what it tries to capture. But it's sort of, I think a good idea is sort of keep your favorite sort of thing of the sort in mind and just sort of think through whether all the axioms that I'm going to write down are satisfied by that thing, and then it thinks down that sort of subcollection. And I completely agree. There's a strong belief, of course, there's a larger thing we should consider. But I'm going to pin down a fairly large subset of it. Okay, so let's sort of write out the definition, put this into context. This categorical spectrum. Connection. Okay. equivalence. So the assumption 0 is basically just saying T50 is form a categorical stack. So this is, if you want, just a nice organizational notion to consider. That is, would make some comments. Of course, categorical stack have appeared in the setting of T50s, I think, for a while now. Some of the early mentions of this is, I think, Konstantin talks about anti-categories. Claudia Scheinbauer has all these towers. This is also unfortunate. They have like 50 different names for the same thing. Okay, great. Yes. Okay. Then I guess I will sort of just talk about anti-categories, basically, yes. And then sort of briefly, there's some cool development in sort of the abstract theory of categorical spectra. Is of course modeled after ordinary spectra and algebraic topology. And it's lots of foundational work by Mr. Beckner-Heine. Which starts to like really pin down the foundation. Of course, as I just said, this is supposed to be a non-invertible version of a loop spectrum. Okay, so next assumption on my collection activities is that the category T50N has all algebra. So formally, of course, this means that if I have a K created in zero-dimensional T50, possibly between other T50s, there's some morphism in my category. What I can do is I can bend this around and resist. So that's sort of X resisting X bar, such like X bar. X. There's six bar. And on the other side, it's fine. That's a fairly reasonable assumption on compute, right? Okay, so far this sort of gives me the sort of abstract category that well-limited work. Right, so this is sort of the setup. Let's go and talk about one dimension. And that shows, yeah.
How much is known how assumption 1 is related to the last, so you define everywhere?
Sure. I mean, if you're defined everywhere and you're fully extended by the course, well, there's awesome.
So, how much is known in general? How much this applies?
Depends exactly on the setup in which you're working. Depends on the kind of category. Yeah, I didn't say in private. I can say something about the skating, but I think that's not going to be the focus here. Okay, so let's sort of declare what a one-dimensional T50 is. So you know, one-dimensional T50 should be a finite dimensional Hilbert space, and that's just it. There's no. I will work with supervector spaces where it brings sort of a more general type. So what I'm assuming is that the function T1 is the handle to your finite dimensional supervector spaces. Again, it can sort of really sort of say in this form, my complex numbers are discrete. I just consider them as discrete. Good. And this is just something I'm assuming.
Sorry, do you need the product and the structure?
No, doing not really start about so. I mean, I think there is an interesting question. Just redo everything here working with sort of cleanly unitarily, but I just do an algebraic stroke. So there's no inner product, I just have a finite dimensional split. So then I want to impose a little bit of additivity. Function three. There's a few functions here. TQT direct sums and zero length lenses. So I can have two TQTs that come together, and there is a zero TQT. More formally, TQT is a semi-active. If you're familiar with this terminology, with this, what it means, there's and it will automatically, because I assume, because everything is sort of these characters will group one another, they're always measured for noise. Therefore, the linearity at the top implies that this is already a linear character. Not like a vacuum with some sort of super. And the other condition that I sort of prove under higher version of additivity, if you like, is that TQT is, this is again, it's a concept that has different names. I'll say one, it's higher. Other names for this it's kind of consistent complete. I'll say a few space. I take a
So another question about the previous assumption. Do we allow all the craziest limits for only filtered one for the profile?
Yeah. So far, I'm not allowed any coordinates. Moment and units have allowed some coordinates, but only very absolutely. Exactly. I'm going to exactly. This is exactly what I want to say. Yes. Which is again the formal condition of this means is that TQT and has absolute with respect to the linear, the sort of absolute over a linearity. Absolute coordinates again. Comment mathematically, if you're familiar with this notion, that's what this means. Absolute means in the setting all the coordinates that are preserved by all other terms. So if you want, these are the coordinates. I mean, intuitively, I think you could have way to think about this. These are the coordinates that you did equation where you don't have to check compare with other things. I think that so you should know it. I should say this notion of higher for complete is developed by Reutter with PhD student in settle. So the setting is infinity categorically, including some relative universal properties. And there's on the TQT side, oriented TQT, there's closely related work. I can't forget the point. And I should also give my sort of physics comment what this is supposed to mean. Physically, what the second condition does is it allows for, or it says that if I have something like a commuting projecting neutron or state sum inside of a TQTA. So giving this sort of projector inventory model, I'm living not just in a vacuum theory where it's a vector space, but I'm living sort of giving ourselves the freedom to place ourselves into TQTA, then this is going to define a new TQTB, and this new TQTB should also be mechanical. So this is sort of the mechanical TQTA should be closed under commuting projected Hamiltonian points. Is what this assumption gives you. And yes.
So there are topologies which is beyond the community project.
Yes. I'm not giving this to myself yet. Yes, exactly.
So the question is whether you that right plus one dimension. The modular transaction category, which is in non-trivial B class.
Yes,
you know,
but this will not yet. I'll put in more assumptions and then at some point. So far, under this assumption, I've just said this is closed under this operation. I've not said that I'm not said all of the objects in there will be built from this from the back. I haven't said that. Right? It's just say if you have a TQTA and I have a commuting projector Hamiltonian model in A, I get a new TQTA. And then this is a thing I can do. So like this is sort of the minimal sort of completion operation. So okay. So let me make another mathematical comment. So this is yes.
So I'm not sure what that's the trouble with that, but doesn't say something called the full product for UFQs?
Yes. So this is the direct sum.
Right.
This is also the
So
product.
they say it's not. That's not regular with like
Yes.
theory you can find the other one.
Yes.
Say the full product.
Yes.
I'm not recognizing what is this thing that you
Yes.
actually these things.
That's right. So this is going to be there's a group OI, which has two objects, and the automorphisms of one is your one group G, and the other one is H, your other group, and you can do a decrypted hidden theory with target that group OI. So you can
The parameters, split parameters from theory.
yes, exactly. And I mean these kind of if you take a direct product, what would happen, for example, is sort of this multi-symptom thing. They sort of decompose into direct product. And so there is some sort of actual projectors around that sort of split. So you might consider this as non-stable or something like decayed. So exactly. Okay, let me get a question.
Yes, you also intend to create non-separable or non-sensitive stuff.
I have not yet said anything about this, but I will, and I will sort of force transactions. So this is the most restriction that we come last. But just sort of as sort of probe the realm of these things. This talk will just be about the same simple set things. And again, the sort of reason for this now is that I'm doing a purely algebraic, discrete sort of non-right story, and this from other perspectives, of course, but I just suppose to let me make one important comment about again a mathematical comment about what this condition really gives us. We are in characteristic 0. So since the characteristic of the complex number is 0, what this implies is, and this was already mentioned, this includes it's a physics version of it and a mathematical version. This includes finite station of finite property of form symmetries. That's definitely sort of if I have a TQT and I have some symmetry, I have one symmetry, and that's something that this also mathematically is being that these assumptions imply that you have ambidexterity or asymmetry. That's almost sort of to get the mathematics going of this construction. That's the key corollary. Okay. Good. Okay. So now so these are sort of this is now the background world. Yes.
I think that relate to this. So suppose you consider a trivial impairment. I need to mention.
Yes.
Then you consider the main wall between full trivial one. So that's supposed to be co-dimension one is station inside trivial one. But you also require is the co-dimension one station including all the TQFT one lower dimension. That's
Yes.
I feel this may be related to this.
I think this is this function. If I'm like the n of the one execute to n, I've decided the domain was from the trivial to the trivial.
Yeah.
And I'm requiring that this is the same data in -1 dimension.
Then the question that if you consider 3 + 1 dimensional figure domain, what is the way of all the one category?
Yes, this will hopefully I get this. Yeah, okay, exactly. So right, so now this is sort of this is the background where I'm working in. Now from the most serious assumptions, there will be 2 more assumptions. One of them is a separate inverted. And this is again safety assumption 4. This is really fluid and hot. And again, gives sort of the easiest digestible version of this. And if they I can look at the group of invertible n-dimensional activities. After invertible domain walls. Which if you want is I0 off to T and GTN is symmetric before it turns out to be symmetric, but no one is going to be of false. Fine there, and I make the 0 of it. And there's a map from here to on the being groups. On the plane. This map is doing this group is a group of safety frame and unflows. I'll just say different orders. And in any symmetric monoid, any groupoid, if I pick up an invertible object in there, I can place that object. That's sort of what n categories allow me to do. And with invertibility, I can place this object on an invertible, on an n-manifold. So what this map is, canonically happens from the assumption that I already made. This is physically for this sort of take your TFT and compactify set on some n-manifold. And this gives me a 0-dimensional TQFTs, but 0-dimensional TQFTs I've already identified with complex numbers. Invertible 0-dimensional TQFTs are invertible complex numbers. And so what this does, you think if it's just the character on the Steffens group, this is the map for the variable repetition function.
So I need to consider frame.
I am considering frame TQFT. I'm considering so far this. Typically, I'm considering frame TQFTs. Mathematically, I've just said this is a category, and I haven't given any sort of additional orientation structure.
Yeah, I see the choice of just action.
That's right. Yes. So I'm considering frame TQFTs. So exactly. Right. And the assumption is so this map you always have. But the assumption is there. It's actually this is sort of the assumption that I'm considering frame TQFTs is that this is. And if you want, the reason I'm considering frame TQFTs is that I can, from this formula, I mean, it's very hard to compute, but formally I get oriented. So this is the assumption, if you want, that's the sort of so far really the most severe assumption, is that invertible TQFTs are determined by the partition function. And again, the mathematical comment, as I think everyone who knows these notions will recognize it and say it anyways. I started with the math. Just by assuming what TQFT0 really TQFT1 is, I have this map also, and I I ask for this map and features an ISO. Extends harmonically to a map from here to the crown prominent. Would cross and ask this thing ISO. That's just, and if you unpack what this means, it's together. And again, sort of this is, if you want, the first time some of these physical conditions really come in and doing framed and discrete. That's what you see. I'm looking at complex numbers that is really linked, and I'm looking at, I'm asking just look at IC for yes. So then I come to the last assumption. So now comes the last sort of severe restriction, and this is synthetic. And really, if you want a reason to impose this, is to sort of get it first. Like, I'm not saying all teachings are supposed to be saying simple, saying let's first look at the sensible ones to get sort of understanding what happens here. So this is assumption 4. Assumption 5. For all one-dimensional domain walls, I think n-1 vertices in PGCN. So I really mean one-dimensional, not co-dimensional one-dimensional. It's really the one-dimensional things, including the transparent attribute ones. I can look at the algebra at n and s. So these are the point operators or local operators that live on this one-dimensional thing effect. And I assume that this algebra is finite dimensional. I would say 7. So this whole story you can do. The important thing for the story is that your characteristic 0, and that is so then at that point. Meaning you need characteristic 0 to get your seniority, your higher seniority, and so therefore it's in center. Really interesting.
Yeah, but sort of also depends on elsewhere culture, which shorts the whole edition algebra.
I mean, the whole story doesn't really well. The field, the base field has to be algebraic. There is a story. I mean, yeah, this is sort of part of large story that you don't need to ask it to be algebraic. Okay, so really, I mean, just for a picture, physically, I'm having some sort of big, collection of these TGFTs and defects and whatnot, and somewhere there's sort of just a one-dimensional line, and this is some one-dimensional TFT relative to all of these sort of higher defects that sort of merge into it. And I can look at the point operators, the local operators which sort of live on this, and I ask that algebra is fancy. I can also make a comment if I would develop a unitary story and I do impose the rigidity that everything is sort of defined in one manifolds and have four duals, then this finite simplicity is automatic. So in the unitary world, if you really want to get around this, you have to drop some of the rigidity. This is an assumption. So this sort of these are all the assumptions. So now you sort of place yourself in the world of those TFTs you know that sort of fall into it. Of course, it's two continuous probabilities and so on, but it does capture some of the TFTs you might like. And the theorem in progress is I think we're still promising that the version of this theorem says it is the way it says a unique categorical expansion. Sounds. So I never had to say anything about modular fusion characteristics, for example. This would all come out of the machinery. Let me make 2 remarks and then say a little bit how this looks like in low dimensions, and then I'm done. I just say 2 remarks. So this is sort of an offshoot, if you like, of a large project. This large project is to build high categorical versions of the separable, like algebraic closure of the category of vector spaces, the categorical spectrum of vector spaces. And you can do this, you can build sort of a separable closure with some Carré extension. Of real numbers, it turns out the complex numbers are not algebraic versions higher world. And this is the spectrum here that I'm getting is not quite the same as the algebraic closure, but really close to it. And I should say the way this is built follows exactly these ideas. So what you do there is some higher version of Kummer. It's actually this is related to work of Thomas, and rather this sort of what larger relation like the Gnosis is. Once with this categorical Kummer theory, and it's sort of an incarnation of these ideas. And right, so if you sort of so this is where this sort of came out of, and from this sort of separate closure perspective or Galois extension perspective, you don't say semi-simplicity, you don't pose it like here, but it comes out of things in the extension. Okay, so I promised to say a little bit about low dimensions. Sorry. So let's look at first of the invertibles, zero of the invertibles. Invertibles can be seen right? So this I posed that just said what they are. So it's the same by assumptions as so the characters in the stable frame posed by contrary form. Here. So you know this low dimension very well, and let's just say how so well. So I want to comment on these dimensions. So these are the invertible 1D TFTs, and it's TFT0 is the complex numbers by assumption TFT1 is supervector spaces. And that's good because invertible objects is supervector spaces, and invertible lines, superlines, even line and odd line is big, but it's so big to it. And let me just point out there is non-invertible stuff in there, of course. So sort of the cool game is now to sort of I'll tell you what this category is. The invertible stuff is clear by assumption. The interesting thing is that this theorem tells you exactly what the non-invertible stuff is. So the indecomposables in here, as I said, are like the even lines and the odd line. And there's no non-zero morphism. So from the perspective, so if you anyways only care about indecomposable series, which is fine, I think it's some of these, there's no more information than this. You have these 2 lines, there's just nothing. But here already something more interesting happens if you run this game and see what T2 of T2 will be. What this will be is the category of complex finite dimensional separable superalgebras and bimotrics between them.
When you say that there's no more vision, not online, but there's no boundary of the connection.
Yeah. You're one dimension higher, I think. I really just think there is that if you take one dimension and it's here too. Yeah. It's just truth now, right? That's just objects. The has changed now object. Putting decomposables here, which are the same as the rootedless C12. There's a trigger and then there's a cliff one diagram. For the complex numbers, right? This one's a C12. If I take cliff one to the cliff one, that's cliff two, which is formally equivalent to the unit by sort of the Clifford algebra version of complex odd periodicity. But what we have, just by how this is split up, there exists a non-zero moves between. Let's get is what is equal. And I mean, from this, if I implement this as superalgebra state, if you take cliff one as a modulo of grade Z, that's a modulo to the unit. So somehow here already more sort of interesting structure has appeared, right? Where here we have the spectrum, and the spectrum you have just C2, this a thing and another thing in the individual form. But in the categorical spectrum, there's something non-invertible. This is sort of a one-morphism that's not invertible, that's hazard. And somehow this later, sort of in this construction, this is always a whole game. It's to sort of understand the non-invertibles by assumption, and you have to sort of understand who are the non-invertible morphisms between these. So here's this game, and playing off this who are the invertibles and who are sort of what I call the components, sort of the components of this category, the indecomposables up to the existence of non-zero morphisms, which in this case is sort of zero. It's outward connected, but there's something non-zero. It sort of guides this whole little. And I want to yes.
To keep it interesting, which assumptions tell you that the speed of can you guess from your assumption that like
so what forces superalgebras to appear is the assumption that from these assumptions, I think it's what forces superalgebras to appear is the assumption of being close and absolute coordinates. This means you have to have sort of you can build your you have to have sort of the sort of this makes cliff one. Cliff one is the data absolute coordinate of the vacuum. And this makes not just cliff one here, it also makes the bimodular here. And then you go and check, look, I already have hit the invertibles. Like this induced natural IC prod is still I0. And then you're like, okay, all my assumptions at this level are already satisfied, I'm done. And then I move one level higher. So let me sort of say, just indicating of how dynamic fields, and here want to sorry. I really avoided W. I mean, at some point we started calling this thing W for no reason. I think because we first called it V, and then we had different construction, and then this had to be called W. It's just not a good thing. So this is getting back to the question of Xiaogang. I should also say you can almost read something about a character which is really closely related to this. China fully local. Which constructs a category which is closely related, sort of a non-framed version. So we're doing sort of the framed version here. And what this turns out to be is, well, let me sort of give you an indication that invertibles are C124. So the next question you can ask is who are the indecomposables ISO say? And what those should turn out to be is weighted equivalence classes of super non-degenerate, okay, modular. So non-degenerate being the frame version of modular. Wait, stop talking about it, really should be right. Anyway, house plus. Okay. Also, there exists a non-zero necessity between them with same element in set. Okay, yeah, I got to say everything I wanted to say. Thank you.
I probably one way. I have the this your assumption. I had yeah, the question is differentiation for something for the guess provided change.
Yeah. Yeah. So the way I think about it, why in the sort of in the second first approach we're not sort of like why assumptions, but the way these assumptions are from your perspective is that so if you start out to kind of reflect says, I said this teaching space given there's some kind of extension of things. There's some kind of some kind of extension. And what assumption one forces to is it tells you that the Galois of this set, the closed thing, has sort of trivial the fundamental. So this is what assumption one is. So what assumption four is going to just say is that it says that this Galois space has trivial cohomology. It's sort of safety trivial. And the way this theorem somehow, not the way the theorem is proven, but the efficient for this theorem is essentially a version of Fourier. So you have the T51 fixes the fundamental proof, and the assumption 4 fixes the Taylor homology type. And together they make a full space. So if you drop assumption 1, you have to somehow say this whole story as a sort of appropriate local system over whatever sort of thing. What makes assumption one good is that S is algebraically close. And if S wouldn't be algebraically close, you could still do something like this, but now you can carry it around there.
So usually we say 2+1 dimensional vertical from knowledge for the group C, but here you can see force is sort of this with job. You carry this for sure, you trivialize the stack in the short copies.
Yes. So what it depends really again on which spectrum you're looking at, right? I mean, if you look at MTSO, then you see I guess set dual, and you see a set in the creek here. So there's sort of two things that come from there. First of all, let's say you want to only advise if you look at continuous accumulation classes, in which case you do see a set in this degree. So that's one way it differs, and the other way is one way it differs is the set that you're looking at continuous accumulation classes. I'm looking at really isomorphism classes, And the other way it differs is that you're looking at oriented theories. Maybe you're also looking at spin theories. They all both have a set, but they are related by C. And I'm looking at spread. So sort of the fact that the CMO 24 appears here is a spreading phenomenon, and it's a I mean, actually, it also appears as if I work relative to say. Even if I work continuously, this will appear as a frame phenomenon. And fine. So the point is just that the set, which would sort of, I guess, in sort of a moral story here, correspond to the lift of the central charge to Q, and not just Q mod square set, is about the fact that you're allowed to look at spin manifold, let's say, or and that if you just work relatively to frame, that is the case, this theory should be less. Let's say the secret again.
And before that, we both like drop. That's good. That's very yeah, probably later. So I pretty much like it.
How did you say it? There's a function that I point to that's not it's kind of the same. Yeah.
Okay, there were two errors.
But then also, as I said, like a very impressive correction.
Oh, okay.
Then you wear like something or some kind of. I don't know. Yeah. Those don't look like flavor. There's no point here anymore. Yeah, I have pointers.
Yeah, are you able to, are you okay, like while we're finding, are you looking at any?
Like this?
Yeah.
Yeah.
Yeah, starting with that. That was very friendly. Where like.
I'll just point with my fingers. Yeah.
Oh, sorry.
Anyways.
Right. All right, everyone. Welcome back. So our next topic is Pelle Steffens, who's going to tell us about some of the math for human symmetry.
Thank you very much. Thank you all for being here this early in the morning, also with the heat today. Apparently only going to be 36 degrees today, so hope you're all dressed warmly. Okay, so we're all pretty familiar with the following picture. I mean, I could put the picture on the slides, but I think we've all seen it many times. Okay, the cursor moves back to the center of the time. Given a finite group, there is an n+1 dimensional diagonal hidden theory associated to this group, which we put in default. Which you can think of as the boundary. Here you can put the regular boundary condition, and theories with G actions sit on the other side of this key, a sandwich. Great. This worked. Fantastic. Thank you very much. And so if you want to tell a completely mathematical story about this, there's at least two ways to do it. So in the case of finite G, the path integral is completely well defined, it's finite. And in the full extended higher categorical setting that we might want to be in, this is nowadays taken care of by the machinery of what's called ambidexterity, higher semi-additivity, developed by, among others, Tomer. Or what one can do is just pick a suitable target. For instance, invented by Hopkins. What it means, you can pick a suitable target. For instance, the high Reutter category of, in this case, k-linear categories, and find some suitable fully dualizable object therein. In this case, the category of G representations. And by the convergence hypothesis, will give you this. So let me remind you that this high Reutter category, this is if you plug in cat infinity, this is an infinity n+2 category whose objects are En monoidal k-linear categories. One morphisms are En-1 monoidal bi-module categories between such two morphisms, which are En-2 monoidal bi-modules, etc. until you get to n morphisms. Then n+1 morphisms are functors, and then there's natural transformation, and then everything is convertible. K is a commutative ring. Okay. So something that a lot of us have been pondering for a while now is what to do if you replace the the finite group with a continuous or a smooth, that is a Lie group, you might want to label defects by infinite dimensional view representations on something like topological vector spaces. So in this case, it's better not to consider categories enriched over R. It's better to consider something like categories enriched over topological vector spaces. So what I want to do today is I want to set up a bunch of such target categories of topological or something like that vector spaces and higher vector spaces. For instance, the higher category, and get an analog of this diacontinuum theory for a compact Lie group. And as for the finite group case, we can do this in two ways. We can either find some highly dualizable object in some category of topological vector, some higher category of topological vector spaces, or we can directly define a functor. That should be something like take a Bornism to the moduli space of solutions to the equations of motion of the theory, and then quantize this. And so here I go from, I hope this is visible, I go from n to n plus 1. So in the continuous group case, we expect the Hilbert spaces to be infinite dimensional, so we cannot do better than n plus 1 dimensional once categorical vector. So here are some physics papers that I put on here. So I should warn you that I'm not a physicist. I'll be using physics words, but it's important not to take me seriously as I do so. These are, I think, the sort of important instigating papers, and I put some collaboration names. I apologize if you should be on this very short list, but you are not. And so these papers tell us that the theory we're looking for is quantum VF theory. Now, classical VF theory. Classical VF theory is a so-called AKSE sigma model, whose target is this shifted cotangent derived differentiable stack. So that's if you don't know, if you're a physicist, you don't know these words. A derived differentiable stack is something like an NQ supermanifold. And a shifted symplectic derived differentiable stack is something like BV theory. And usually in this passage from what mathematicians call derived geometry to BV theories, there's some lots of information. You go from a global moduli space to something perturbed or something formal. So in this case, the formal neighborhood of this thing is just this product of the algebras. For n equals 3, this target is exactly the classifying stack of the cotangent of G. So for n equals 3, this VF theory is transilence for this cotangent. So if you were at the meeting in New York last November, this might all be very familiar, because what I'm saying now is just essentially what Dan Fried was saying in his talk there. And what my talk is just essentially an elaboration and an explanation. What attempt to make precise some of the things he said in this very nice talk. I think it's on the, maybe not on his website, but it should be on the Simon's website. I'll also flag the following very nice paper. So in some, a lot of the machinery that I'm going to be talking about is already set up in algebraic geometry for algebraic groups. And Devin, who's here, and Matt, who has left, I think, have used this similar sort of ideas to set up what I'm going to be talking about, but in the case of algebraic groups. And there was this very nice paper by I think a student Chang Chung. Maybe we should talk about this paper. There he is. Yes. I really like your paper. What's your first name? How? How very nice explained how in how this the scientific story fits very nicely in sort of classically in the framework of derived symplectic. Okay. Yes. What is the code?
What is the
Maybe now it's going to. So this is the. Oh no. I do this.
Yes.
And then I click this. Okay, it's vanished. And now so how do I prevent this from happening? Like, what do I not do? No. So BG is in the world of mathematicians. This is a smooth stack sheaf on the side of manifolds. I can view this on a larger pattern, on a larger sheaf on a larger category, sheaf on the side of so-called derived manifolds, which you should think of as on so-called derived manifolds. So you should think of these as like a homotopical version of non-homologically, non-negatively graded NQ supermanifolds. So in that sense, you can take the cotangent of this object and you can shift it. And you should, well, like this is sort of the tangent of this object at 0 is this the object. I'll come back to the players in this slide.
Okay. The right hand side also there was equal the then the other group.
But the cotangent of a Lie group is again a Lie group, which is G semi-direct product with, so G acts on the dual of. Let's hope this goes well. Yes. So what are we going to do? So I'm going to follow essentially sort of an algebraic geometric paradigm. You get a lot of mileage out of thinking of rep G as quasi-coherent sheaves on BG. So here BG is a slightly different thing than on the last slide. Here G is an algebraic group and BG is an algebraic stack. So a sheaf on the side of sheaves over something. And the geometry of BG will tell you, and sort of good properties of this construction Q code will tell you that rep G is a highly dualized object. Category so here now I'm talking about not like in the fine group case, you might think, okay, let's take representations on fine dimensional vector spaces. Here I'm taking very large category G representations, and for the mathematical place to do algebra with categories is this will presentable higher categories, and I will say a bit more about what those are, but for now just treat this as a black box. So the idea is to emulate this construction, find a good notion of quasi-coherent sheaves, but for manifolds, or these more general derived manifolds. So what should this roughly be? Some kind of derived category of modules for the ring of smooth functions, suitably enriched in some notion of topological vector space. Right? And then we define rep G as Q of BG, now for BG being the smooth side. And hopefully we can transfer the same properties same proofs that we have in algebraic geometry to this differential geometric setting. Any questions about this? Or no? Okay. So the rest of the talk will consist of 3 steps. So we're going to spend probably quite a bit of time on explaining what I actually mean by topological vector space. So we need some good category construction. We want to do higher category theory. We want to do homotopic theory, homological algebra. So this category better be abelian, and also we would like it to be presentable. There's some excellent candidates that have been developed recently and not so recently by some members of the audience. Yeah, and I'll take some time to explain this. Then I want to construct this BF theory for a compact Lie group by the cobordism hypothesis, and then if time permits, I'll construct this by quantizing this by this last theory, just as we had for finite. So much of this work is in is joined with Claudia Scheinbauer, Jackson Van Dyke, and Paul Stewart. Jackson over there. In particular, for full applications to what I'm going to say today, and a better, more grounded sense of the physics, what's going on, I invite you also have a look at Jackson's poster in the room that has the poster. So now I want to explain what I mean by this category of topological vector spaces. So what should we take for this? So from your functional analysis lecture, you might expect a reasonable choice to be something like Hausdorff complete local convex space. Right, Hausdorff complete, like we want there to be, we want to have some kind of complete template, so the space better be complete. Hausdorff is like, okay, we want to have unique limits for sequences. And locally convex, well, this allows you to construct a lot of functions by down route. I call this before. So categorically, let's rephrase this notion of categorically. Turns out that these are built up from Banach spaces in a particularly controlled way. So given such a thing, a locally convex space, the topology is induced by a system of seminodes, and you can recover the